Det var en fantastisk præstation og en fantastisk inspirerende videreformidling af, hvor det er, vi skal hen, og hvor vi kom fra, ikke mindst. Inden jeg præsenterer den næste taler, så vil jeg lige præsentere Mie Nørgaard, som står herovre. Hun er illustrator, og hun tager nogle hovedpointer fra alle de taler, som kommer op her og får det ind i sin tegning her, så når der er pauser, kan I jo gå hen og smugkigge på, hvad det er, hun får ud af, hvad talerne kommer med her. Vores næste taler er allerede på scenen. Han kommer fra Oslo Universitet, hvor han er professor i fysik og leder af Center for Computing in Science Education, og det er Anders Malthe-Sørenssen. Og jeg forstår det sådan, at du er en pioner, når det gælder det her med at få computing ind alle mulige steder til også at forny indholdet af undervisningen. Ordet er dit.
Thank you. So, can you hear me? So I've decided to speak in English because when I get excited, I often talk quickly, and then if I speak Norwegian, you won't be able to understand what I say. But I think the introduction was sort of perfect. That language really shapes our thought. And this, as a physicist, this is a real problem when I try to teach my students. Why? Because the language of mathematics has very limited tools if you don't use any computational tools. And my thesis is that for the last 500 years, that's basically shaped the way we teach physics and many other subjects. And it shaped it in a way that we don't necessarily sort of agree with if we think carefully about how we would like to teach the various subjects. And this is going to be a very essential point in what I'm going to talk about. But I'm going to start essentially from what has been said already, that computing has changed the way we practice science and the way we practice almost every aspect of all practices in society. What's then very surprising is that it's not really changed educational content. What I mean by that? I mean, if you pick up a typical textbook in physics, it's basically impossible to see that a computer was invented in some sense. It's almost identical to the way it was 50 years ago. It's not completely true. I'm being a bit, putting it a bit to the point, but it's mostly true. It's not really reflected in how computers and the use of computing is not reflected in the material that we use for teaching. And this is a challenge. But it's also an enormous opportunity. We are now in a situation where we have the opportunity to rethink the curriculum in our own disciplines. So for me as a physicist, this is sort of fantastic opportunities. This is basically once in a lifetime or once every 100 years. I get to rethink how should we teach physics now that the computer is part of the toolbox of the students. So this is something that should inspire me and not frighten me. Of course, it's going to frighten me as well, but it does really inspire me. There's an opportunity to now develop new contents, change the way I'm teaching physics, and also to change the aspects of physics. So one thing, I come from a field called statistical physics. We are very interested in, for instance, diffusion. So diffusion is sort of atoms diffusing around. Diffusion is something that students don't learn about in the K-12 system. Why? Because we can't solve the equations. Not because the process is not important. It's extremely important for all biological processes. So this makes it almost impossible to connect biology to physics in K-12 because you lack some of the tools. Not because the processes are not important. So this means that we are now able to start to think, how can we integrate computing into the various disciplines, into the disciplinary contexts? And then we need to be a bit careful, because I can say something about physics, but I can't really tell an economist how to change the sort of his discipline. And I can't tell a bioscientist how to change her discipline, for instance. So we need to work together. And what turns out to be really tricky is to develop this type of interdisciplinary collaboration in education. I mean, it's really difficult in research or innovation. It's even more difficult in education because we have so long traditions of doing this completely separately. So I'm going to give you some impressions about what we've been doing at the University of Oslo, and the current status there is now that across the science curriculum, computing is integrated from day one. What does that mean? It means that when students start, they get a programming course in the first semester. The physicists get it, chemists get it, and the bioscientists get it. But it's adapted to the specific disciplinary context. We tried the opposite. So from 2003 to 2007, physicists, they took an ordinary course in programming. And then when they came to physics, it turned out it was very difficult for them to transfer the knowledge that they had in ordinary programming to solve a problem in physics. And we know this in education research, that transfer is maybe the most difficult part. So why didn't we think about this when it came to computing as well? Well, we did, and then we changed the course. So now we made an introductory course in computing for students who feel safe when we talk about mathematical problems. Okay, this is well suited for physicists and mathematicians, not for bioscientists. Okay, so if you go to bioscience, you need to make a course where you start with bioscience type problems that motivate students, and then you bring computing in through those problems. So we start with this in the first semester, and then what we try then to do is to then inject some computing into the remaining courses as well. Why? Because you learn what you do every day. So if you want students to really learn this, we need to integrate it in their activities. Our ambition is not to train everybody to be computer scientists. We want to train students to work in their discipline, but to have the increased toolbox that includes computing. But then they need to use it every day as part of their activity. So it becomes part of their identity as a physicist or as a bioscientist. When we do that, we try to divide the bachelor timeline, and I'm mostly going to talk about the bachelor studies now. So the first year, we mostly focus on what I would call fundamental skills, and some start with this sort of contextual integration. And then gradually we move towards higher order skills. So this is sort of higher order skills in the Bloom's taxonomy, relating more towards creativity. Authenticity is something that's close to the actual practice. We solve realistic problems and what we call student agency, that students take ownership of their own learning process and ask questions, closer to what you would call the research process. So how does this look in practice? Now I'm going to give you a few examples. So in the first semester, for instance, we integrate across various disciplines. So in the first semester, all students take one course in calculus, one course in numerical calculus, and one course in programming. And then each week we have once all the teachers met, and then they agreed on the schedule for the first semester. And then they figured out that if you teach in calculus, you teach the concept first, and then you teach the week after the same concept in numerical calculus. And then the week after that, you implement it in the programming course. And the students report that this course, so this semester, is probably the most integrated semester they've ever seen. All the teachers only talked once, so it's you don't have to do that much to excel. Okay, let me provide you with a few examples, very specific examples now, about how to do how this is done in physics. So let me start with one example from physics. So this is the most classical example in physics. It's what all physics students need to know. It's called ballistic motion. And all students, they need to figure out how to use Newton's laws of motion, or Newton's laws, and separate it into horizontal and vertical motion. So this is part of the culture of becoming a physicist. The problem with that is that when students do this, they spend most of the time not on physics, but on solving the mathematical problem, to figure out, for instance, how far does the projectile go. And my problem with that is that they spend time on mathematics, nothing wrong with that, but I really want them to think about physics. And then they end up with a solution, which I printed in the bottom there, which is closed form. What does that mean? It means that this solution is, when they get to it, it's either correct or not. Typically it's not correct. There's a factor 2 somewhere, and they need to rewrite everything, go through those 3 pages of calculation. So they spend a lot of time not on discussing physics. And if they got it right, they just tick off and move on to the next problem. There is no reflection in this process. But we could reshape this, we could redo it in a different context. So typically we can introduce students to this. This is a picture from the movie Twister from 1994 with Helen Hunt as the main role, as a tornado chaser. So her role is to drive this car into the tornado full of small probes, and then the probes get caught up in the tornado, and she tries to measure the velocity field of the tornado. Okay, so we can ask the students to do the same thing. We can provide them with the velocity field of the tornado, and then we can ask them to figure out how should you shoot your probe through that tornado. And then they learn exactly the same. Why? Because they learn how to use Newton's law of motion and gravity, But in addition, they need to include the area assistance into this equation. And then they end up with something that you can always only solve using computing, but that you test by comparing with analytical solution. And this completely changes the dynamic in class. Why? Because students, when they try to solve this, all students get different results. And this is good, because then they have to discuss to figure out why did we get different results. Is it because there's something wrong? Or are both sort of results equally good? And how can I figure out if my result is good or not? And this discussion is this type of scientific discussion that we want students to start to engage in. And even better, students always want to experiment. Okay? So they've seen a different movie. They've seen this movie as well. If you know the beginning of Forrest Gump, you know there's a feather moving around, and then finally the feather lands in his hands. Okay, so all students want to try this. They started with the probes, but what happens if you inject a small feather into the tornado instead? So students want to experiment. They want to be creative. They want to try out the limits. Another aspect of that is also that this provides me as a teacher with a way to look into the minds of the students. Why? Because when they write the program, it tells me something about how the students think, their thought process. So by looking at the program, I get a different way to see how students are reasoning. And it also forces students to reason. I ask students always, do you understand friction? Okay, all my students say, yes, of course, I understand friction. And then I ask them to write a program for a block that slides up an inclined plane. And typically among 200 to 300 students, 1 to 2 students are able to write that program because their understanding of friction is not that good. They are not able to when they actually have to formulate it very precisely, it turns out that it's not that good. Why? Because the computer is probably the most stupid co-student you can have. You have to be extremely precise when you try to explain your understanding to the computer. So this is the way to think of it. You have to try to explain your understanding to the computer. We try to do something similar in a course in economics as well, and this is me just dabbling in a completely different field, so beware. So we start with a completely classical approach. This is typically the first chapter in any book on managerial economics. It's how we calculate revenue. Okay, how can you maximize revenue? And for that, you need to have the demand curve. How many objects can you sell as a function of what's the price depending on the number of objects? And then you develop a theory based on this. And the theory is very nice. Everything is linear. It's easy to optimize and find optimal revenue. But we can start in a different way. We can start by asking all the students, how much are you willing to pay for this particular bag of sweets? And then we can just collect all the data, and that is basically the demand curve. And then we can use that, and we can fit a curve to it. Or we can find the revenue directly. So then students start to explore directly in the data. And what's even better is that then they also discover that the theory is not really correct. There are some problems with that theory because some of the students don't want to buy this bag of sweets. Okay, so their price is 0. And some are really hungry. Those are the 2 guys on the top left there. Okay, so they are sort of completely out of the range. And this doesn't fit with the theory. And then you have to discuss, what about my theory? How can I actually get this curve? Because finding this curve in economics is really difficult. But it tells you something about how you can start to work with these ideas also using computing, basically. We've done similar things also now in the humanities and social sciences. We have an honors program at University of Oslo, where we also have humanities and social science students together with their science students. And there we can experiment with the students, basically. So we developed a course in algorithmic thinking for the humanities. Okay, you can't call it programming for the humanities, obviously. Must be something thinking. So algorithmic thinking, it's like computational thinking for the humanities. We tested it out first on 20 students, humanities students, and then actually the year after we scaled it to a full level course, which now given to all the humanities. And then we have a course in the semester after. So all the humanities students, they learn to program some basic programming skills. And then the semester after they work together. So the social science students, the science students, and the humanities students work on what we call data-driven projects. Then we take in data from the various disciplines and we analyze them. Then they come together. There are also some aspects of interdisciplinary learning there, but I'm not going to discuss that. Let me just mention one final example. Let me say one thing, additional thing also. We also worked quite a lot on how to get these type of changes. How do we sort of instigate them? How do we inspire change? And we have sort of created what I call a playbook for how we work with various groups in order to try to get the ideas to spread. And this sort of illustrates this playbook where we go from initialization, where we sort of talk to the groups, early adoption, where the groups start to work with this, whereas universities, adaptation, where they actually start to do it, and then integration, where they becomes part of their own activity and they actually start to develop their own material and spread it themselves. And how do we sort of get that running? Well, we have several different initiatives. One of the initiatives is related to how we're financing student groups. So when we developed this course in the humanities, what we did was that we provided funding for 2 science students, 2 humanities students, 2 faculty in humanities and 1 faculty in the sciences to go together and create this course. So we financed that. It is not that much financing, actually. We financed that and sort of put up the boundaries, for the boundary conditions, and that started the activity. Now, in addition to that, in order for these students to be able to create good learning material, we also integrate all the students that are acting as learning assistants into what we call the Learning Assistant Program, which is inspired by a program from University of Colorado Boulder, where you think systematically on how to provide learning assistants with pedagogical competencies. Why? Because of several reasons. They become better teachers, but also in the long run, the students are going to be the new teachers. Okay, so then they start to build up this type of pedagogical competencies early on. And in addition to that, we're also trying to train our own faculty. So we are organizing, for instance, summer institutes where we bring together faculty from across Norway or from across disciplines. The next is going to be probably in biosciences, and then we'll have one in the humanities, together with Humboldt and other circle universities. And then we do two things. We teach them how to integrate programming into their particular discipline, but 50% of the time we just spend on basic pedagogical training. We don't tell, okay, there might be somebody of you here now, but we don't tell them this, but the part of it is just basic pedagogical training. Because the pedagogical principles are basically the same. They don't really change, even though we have to teach computing. We've also redesigned some of our learning arenas, created these more flexible rooms for active engagement, which is done all over the US, for instance. These are it's quite a lot of experience in how to design this to have good, effective group discussions around the screen, for instance, or around the coding you do, and how you connect that to various types of disciplinary activities like experiments in physics or in biosciences. And then I mentioned, so these are sort of the basic skills. I also mentioned these more advanced skills, creativity. Let me just mention slightly creativity. One thing that we have been doing now in the 3rd semester is that we ask students to write what we call a computational essay. Essentially, we say to the students, select a problem, find the problem you like, explore it, and write the computational thesis about, essay about it. What is this thing, a computational essay? Was an essay that also includes computing. And then you're supposed to present it in an authentic setting, which is the setting of a research group. So this student, for instance, here, he created a model of lightning. And then when he presented the model, somebody asked, well, what if you reverse the polarity of the cloud? And then they can just reprogram it and they can immediately see the new result. So it opens again for a different type of interaction. But if you ask students, what do they think about this? They focus on something quite important, namely that usually they're mastering the ordinary activities quite well. So this student, for instance, one of the students participating, he says, I take these subjects because they don't require anything from me. This is a bit worrying. For me, it should be challenging. Okay. In a way, I can just solve the problems and be done with it. And that's comfortable. Okay. We don't want students to be comfortable. But the fact that it requires some creativity is maybe it becomes closer to the way it's actually to do physics. And I feel like this assignment here, it recreates the situation when one has to invent something. One has to find something out, figure something out in a way. And it's not often we encounter that in our STEM courses here. Okay, this is important to me as a teacher. They don't actually encounter the possibility to be creative when we try to explain to them that science is something that's incredibly creative. But they never see this as students. Okay, this is really worrying. And another thing that students also say is that what they really liked about this is that if they weren't able to solve the problem, they can just reformulate the question. Okay, cool. This is what we do all the time. I mean, I know about this. But it's cool that they actually discovered this, that the problems aren't necessarily given. You can change them and you can find something else that's also interesting and you can maybe solve it. So we invite students into this type of scientific discourse. Okay. We have sort of created an environment to address these things. So we are in Norway, we have centers of excellence of research, but we also have centers of excellence in education. So we have gotten a lot of resources to do this. And when we got those resources, we essentially prioritized these 4 areas. We work on developing material and methods, but we also built up an educational research group, which actually is quite important for us, because that gives me as a teacher quite a lot of understanding of the underlying processes, what goes on inside the mind of the student. And I can change the way I teach. But it also provides me with a different types of arguments for how teaching should be designed, because I actually have research to support it. So currently we have now 2 permanent faculty who are doing physics education research, and then we have 1 postdoc and 4 PhD students in this group that are essentially working on trying to understand how computing is changing the way we think. And this is only in physics. It's mostly in physics. Then we also work on building a culture for this, which is really important. How do you spread this? How do you build this culture for how we are doing this type of development? Yeah. Now I just focused on one small part there. I focused on essentially bachelor education. There is a larger picture. There is K to 12, and then there is also the PhD and the postgraduate level. I'm not going to talk about it, but if you just come to me in any of the breaks, I can discuss this more. We also have activities on the K to 12. In Norway, it's the math teachers who are responsible to teach all students how to program. So we have 30,000 math teachers in Norway, and they don't know how to program. Okay, and they should have started this 2 years ago. So there is a scaling problem here. And then, of course, you also need to teach PhD students and postgraduates the same type of competencies, and we need to think about how to do this in a reasonable way. I think that's basically where I would like to stop. So thank you for your attention.